In this section, we'll talk about what it means to solve a differential equation. So the general form for an nth order differential equation with x an independent variable and y a dependent variable can be expressed as the following equation. So it's one big function of x, y, and then the derivatives of y up to order n. And you can set that equal to 0. Now, we assume that this equation holds for all x in an interval, and this interval could be the whole real line from negative infinity to infinity. And in many cases, we can isolate the highest order term and rewrite number 1 as follows. It's the nth derivative of y with respect to x is some kind of function of x, y, and then lower order derivatives of y. Now, to find an explicit solution to this differential equation means the following. A function phi of x that when substituted for y in equations 1 or 2 satisfies the equation for all x in the interval I is called an explicit solution to the equation on I. So that's really important, that we don't want to solve this for one value of x. This equation has to hold for all x in an interval I. So let's do an example here. So we want to show that the function phi of x equals x squared minus x to the power negative 1 is an explicit solution to the linear differential equation second derivative of y minus 2 over x squared times y equals 0. And then we also want to show that psi of x equals x cubed is not a solution to this equation. So the first thing is, let's try to figure out what we have to show. So if we want to show that phi of x is an explicit solution, we have to show that when we plug in phi for y, we get an equation that's true on an interval. So we have to show that the second derivative of phi minus 2 over x squared times phi of x equals 0 on some interval. Okay, so let's start that. If we take our original function phi of x, that's x to the power 2 minus x to the power negative 1, and then let's take a look at phi prime of x. That's 2x, the 2 moves to the front, we subtract 1 from the exponent, the power rule, and we get 2x. And here the negative 1 moves to the front, that becomes a plus, and then to the power negative 2, and then phi double prime of x equals 2 minus 2x to the power negative 3. Now note that we don't need phi prime for the differential equation, but we do need phi prime to get to phi double prime. Okay, so now let's plug this into our differential equation. So for the phi double prime, we get 2 minus 2x to the power negative 3. And then we're subtracting, let me change the color. We're subtracting 2 over x squared, and then we're setting that equal to 0. And oops, So here we're plugging in phi of x, right? So that's x squared minus x to the power negative 1. Okay, and now we'll have to simplify this sum. So 2 minus 2x to the power negative 3, and then think of this as negative 2x to the power negative 2 times x squared minus x to the power negative 1. And we're now asking, is that 0, right? So now we have to distribute this. So we'll keep this for now. And x to the power negative 2 times x to the power 2, we add the exponents when we multiply. And so negative 2 plus 2 gives you 0. And then x to the power 0 is just 1. So that first part just gives us negative 2. Maybe I'll just write this out like this so you can see where that comes from. And then for the second part, we have negative 2 times negative 1. That gives us positive 2. And then add the exponents, so we get x to the power negative 2 minus 1. And then the question is that 0? Okay, so let's simplify this a little bit. 2 minus 2 to the power negative 3. And then, as said before, this is just x to the power 0 or 1. So that's minus 2. And then we have plus 2 x to the power negative 3. And that equals 0. And now you can see that the positive 2 and the negative 2 cancel out, the negative 2x to the power negative 3 and the plus 2x to the power negative 3, it all cancels out on the left. And so this was a question mark, so we now actually see that 0 equals 0. And so this is a solution. Now, to figure out where it's a solution, so this is an identity, we have to see where the original function is defined. So one thing to notice is that when you have x to the power negative 1, that's the same as 1 over x, and this is not defined at x equals 0. So even though this is an identity, it's not valid for all real numbers. And so what we can write here is that this solution is valid on negative infinity to 0 or 0 to infinity. Okay, now let's show that psi of x equals x cubed is not a solution. So let's take that function, right? So we're going to let psi of x equals x cubed. Then we're going to look at psi prime of x, and that's 3x squared. And then we have to look at phi double prime of x equals 6x. So now we're going to substitute that into this differential equation. Here's the second derivative of y. So we're going to use phi prime. So we're going to have 6x that comes from here, and then minus, and let's use a similar color. So minus 2 over x squared, and then equals 0. So what are we multiplying that last part by? That's going to be our original function, so that's going to be x cubed, right? So 2 over x squared, and then we plug in x cubed, and let's simplify that. We have 6x minus, and then the x squared and the x cubed, we get some cancellation going on. So that's actually negative 2x equals 0. And then we have 4x equals 0. Now, again, this was a question mark, right? And that question mark here, what we're looking at is this side always equal to 0. Well, obviously you can solve this by dividing both sides by 4 and get x equals 0, but this 4x is not identically equal to 0 on an interval. So let's write that down and see that it's not a solution. So this does not hold on an interval. It is only true when x is 0. So the conclusion is that psi of x equals x cubed is not a solution.